Welcome back. Today, we're digging into some really cool AI research about understanding how our cities change visually over time.
Yeah, we're looking at a paper called Visual Chronicles, using multimodal LLMs to analyze massive collections of images.
And it introduces this system, Visual Chronicles, that uses multimodal large language models, MLLMs, to find visual trends.
The key thing is, it does this across millions of Street View images, and crucially, without any predefined labels.
Imagine that spotting changes across whole cities,
Yeah.
automatically, just from pictures over years. That's really the core idea we're unpacking today.
And the scale involved is just huge.
Right.
We're talking, what, 20 million Google Street View images
Okay.
for New York City and another 20 million for San Francisco.
Wow.
Spanning 2011 right up to 2023. It's an enormous visual history.
And the system does this open-ended discovery, you said, so it finds trends without being told what to look for?
Exactly. It can spot things like, say, the rise in outdoor dining or maybe an overpass getting painted a new color. All stuff it discovers on its own. And the real innovation here seems to be how they tackle that massive data set. They sort of break the problem down so the MLLM can actually handle it.
Okay, so for anyone wanting the quick summary, the 1-minute version, Visual Chronicles uses these powerful AI models, MLLMs, to scan tons of time-stamped Street View photos.
Yep, and it finds common visual changes happening across a city.
Things like outdoor seating popping up, or that blue overpass example, all found automatically, no labels needed.
And the trick is breaking down that huge data set into manageable steps for the AI.
Okay, great summary. Right, let's get into the details of how they actually manage this. So first off, just thinking about analyzing that much visual data and doing it in this open-ended way, that sounds incredibly difficult. Why can't we just use, standard computer vision techniques?
That's a really good starting point. Traditional computer vision is great for specific tasks, right? Like detecting cars or pedestrians. You train it specifically for that.
Sure, object detection and things like that.
Exactly. But when you ask a much broader question, like what's changing visually across the city, those methods kind of hit a wall.
Why is that?
Well, typically you need to tell them exactly what to look for beforehand. And often you need tons of labeled data to train them.
Right. So if we wanted to track outdoor dining, we'd need a model specifically trained on images labeled outdoor dining.
Precisely.
But what if we don't know all the interesting changes? What about the stuff we haven't even thought of looking for?
That's the problem. You need something that has a more holistic understanding, a semantic understanding of the scene. Meaning it needs to grasp concepts like figuring out a shop has closed just by seeing boarded up windows, even if there's no closed sign. It needs to interpret the scene's meaning.
Okay, that makes sense. And you mentioned the scale tens of millions of images. You obviously can't just feed all of that into an MLLM at once, can you? Even the big ones.
No, absolutely not. Even something powerful like Gemini 1.5 Pro has context limits.
Right, the token limits.
Exactly. For images, that might translate to maybe roughly 8,000 images at a time, something like that.
Which is tiny compared to 20 million per city.
A tiny fraction, yeah. So just brute forcing it, feeding everything in, not feasible. Computationally impossible, really.
Okay, so that's the challenge. How does Visual Chronicles get around it? The paper calls it a bottom-up hierarchical system. What does that mean in practice?
Think of it like building with Legos. You start with the small bricks, the local changes, and then you assemble them to see the bigger structure, the citywide trends.
Oh.
So it's a two-step process. Step one, detect local visual changes using small sets of images from the same place over time.
Like comparing photos of one street corner from 2012 and 2015.
Exactly. And then step two, take all those millions of individual change descriptions and figure out which ones represent larger recurring trends across the city.
Breaking the big problem down.
Yeah, breaking it down. And the key idea they rely on is that MLLMs are actually quite good at analyzing those small sets of related images to spot subtle, meaningful changes.
Okay, let's unpack that first step then. Using MLLMs for local change detection. How does that work practically? What goes into the MLLM?
So you take a sequence of images, say Google Street View shots of the same spot, maybe one from 2011, one from 2014, one from 2017, all from roughly the same location.
Okay.
You feed that sequence into the MLLM.
And what do you ask it? What's the prompt?
The prompt basically asks, what changed in this sequence, and between which images did those changes happen?
Okay.
Figure 2 in the paper shows a good example. The MLLM might look at the images and output something like, between image 1 and 2, a tree was removed, or between image 2 and 3, a new bike lane was painted.
So it's not just saying different, it's describing what changed and when, semantically.
Exactly. And importantly, it's pretty good at ignoring the trivial stuff.
Like shadows or leaves on trees changing with seasons.
Right. Changes in lighting, time of day, seasons, it tends to filter those out and focus on the semantically relevant changes. A new sign, construction starting, that kind of thing.
Okay, so step 1 generates millions of these descriptions of local changes. Over 3 million for NYC, the paper says. That's still a lot of text data. How do you find trends in that?
Right, that brings us to step 2, visual trend discovery. And yeah, you can't just feed 3 million text descriptions into an MLLM either. Still way too much.
Still a contest window process.
Exactly. So they use another 2-part approach here. Trend proposal and then trend verification.
Trend proposal. So it suggests potential trends first.
Sort of, yeah. It takes all those text descriptions of local changes.
The tree removed, bike lane added things.
Yep. And it converts them into text embeddings, numerical vectors representing their meaning.
So similar descriptions end up close together in this vector space.
That's the idea. Then they use a fast clustering method, canopy clustering, to find rough groups of similar descriptions. These groups become the initial trend proposals, like maybe a bunch of descriptions related to new fence cluster together.
Okay, that makes sense for getting potential candidates. But the paper says just using embedding distance isn't enough for verification. Why not?
That's a crucial point. Embeddings are good, but not perfect. Subtle differences in meaning might get missed, or things that are conceptually similar might not be that close in the embedding space.
Like new cafe opened versus bakery became a cafe. Similar, but different wording.
Exactly. Plus, the descriptions themselves can vary in detail, so just using a distance threshold on embeddings is tricky and not always accurate enough for confirming a real trend.
So how do they verify these proposed trends accurately without checking millions of descriptions one by one?
This is where the MLLM comes back in, but smartly. Instead of asking the MLLM about every single change description for every proposed trend, which would take forever.
Right, completely infeasible.
They use a hybrid approach. First, for a proposed trend, they use the embeddings again to quickly rank all the local change descriptions by how similar they are to that trend's core idea.
You get a ranked list, most likely matches at the top.
Precisely. Then, they only send the top most similar descriptions, say, the top 1,500, as mentioned in their experiments, to the MLLM for verification.
So the embeddings act as a fast filter, and the MLLM does the detailed check on the most promising candidates.
Exactly. The MLLM gets the images associated with those top changes and the trend description, and it makes a much more informed decision about whether they truly belong to that trend.
That sounds much more efficient.
Hugely efficient. They estimate it reduces the MLLM computation by something like 2,000 times compared to checking everything. It makes the verification step scalable.
Okay, really clever. So the big question, how well did this whole system actually work? What did the evaluations show?
They did quite a few comparisons. First, they compared it to just asking an MLLM, like, what visual trends happened in NYC without showing it any images. The MLLM gave very generic answers, things like more focus on sustainability or store closures. Very abstract, lacking the specific visual grounding.
Unlike Visual Chronicles finding solar panels added or overpass painted blue.
Exactly. The visual grounding makes a huge difference. They also tried feeding random subsets of images around 8K, the context limit to an MLLM.
How did that go?
Not great. Because each subset was so small compared to the whole dataset, it mostly found only super frequent things like scaffolding appearing and disappearing. And it didn't find many trends overall.
So the two-step approach really seems necessary. What about evaluating the steps individually? How good was the local change detection?
They tested that carefully. They created a labeled dataset. Humans looked at image pairs for 200 locations and marked the changes.
Okay.
Then they compared Visual Chronicles using Gemini 1.5 Pro against other methods like older image feature techniques, HOG, color histograms, other embedding methods, ECFP, NVM, even a remote sensing technique.
And the result?
Visual Chronicles blew them away, pretty much. It got an average precision of about 76.6%, whereas the baselines were mostly down in the 16-26% range.
Wow, big difference.
Yeah, and they reported high precision and recall too, around 81% and 90% respectively for the MLLM identifying those local changes. It shows MLLMs are really good at this fine-grained visual comparison task.
Okay, so step 1 works really well.
Yeah.
What about step 2, the trend discovery? How do they measure that?
That's trickier because, as we said, you can't just ask the MLLM for trends from millions of descriptions directly.
Right.
But they did evaluate the MLLM's performance in the verification part of step 2. It was accurate about 86.6% AP at deciding if a specific local change belonged to a proposed trend.
But the issue is doing that millions of times.
Exactly, the scalability. So they showed their hybrid approach worked well. It achieved high accuracy, like 93.9% for classifying the top 50 proposed trends, much better than baselines. And crucially, it was fast enough, like 4.6 hours, to verify 200 trends using parallel MLLMs.
So accurate and practical. Okay, let's get to the fun part. What actual trends did it find in NYC and SF?
This is where it gets really interesting. Doing that open-ended search from 2011 to 2023, in NYC it found things like 745 new security cameras appearing.
Okay, just a second.
And 509 instances of new fences going up around parking lots. Also, 519 new red warning pads, the ADA ones on sidewalks.
Things you might not notice accumulating unless you look systematically? What about San Francisco?
In SF, big numbers for solar panels, over 1,500 new installations detected, also 751 bus lane conversions, and almost 1,800 new bike racks.
Wow, 1,800 bike racks.
Yeah. And for each trend, you get the image pairs showing the change and maps showing where it happened most. Really valuable visual proof.
That visual evidence is key. The paper mentions being careful with interpretation, though. Potential biases.
Yeah, a fair point. Like the solar panel example, maybe they're just easier to see from highways and street view, so it might slightly skew the perception of ground level installations. You still need to consider the data source. But overall, it's a powerful data-driven view.
They also look specifically at SS since 2020, right? Focusing on more recent changes.
They did a time-conditioned search for 2020 to the end of 2022. And unsurprisingly, a huge trend was outdoor dining structures.
Makes sense, given the pandemic.
Yeah, storefront added tables and chairs outside. It happened nearly 1,500 times in that period, compared to under 700 times in the 3 years before. Clear pandemic signal.
Any surprises in that period?
Yes. The support of the overpass was painted blue trend. Happened 481 times since 2020, but only 5 times before that.
That's the one you mentioned earlier.
Yeah, and it turns out it likely corresponds to a specific project painting the Central Freeway Coronado blue. Amazing that the system picked up such a specific, localized event just by looking at pictures across the city.
That really shows its power for discovery. Can it do more targeted searches? Like only changes related to retail stores?
Yep, they demonstrated that too. They did a subject-specific search in NYC for changes involving retail stores.
Oh.
Using embeddings first to filter for descriptions related to retail, then MLLM verification. They found trends like 512 new bakeries opening, 318 new juice shops.
Interesting. Any closures?
Yeah, also closures, 741 grocery stores closing, and a really high number, over 1,600 bank branches closing. It gives you this quantitative look at the shifting retail scene.
Fascinating. And it's not just about changes over time, right? They did a non-temporal query, too.
Right. They tweaked it to ask the MLLM to find unusual things in single images, not comparing across time.
What did it find?
It kept flagging large abstract sculptures in NYC. It's like the AI developed a sense of what's visually typical in a city scene and could spot the outliers.
That's really cool. And the supplementary material had spatial stuff too, like construction hotspots.
Exactly. They could map out where trends were happening, like new building construction clustered in Brooklyn, Long Island City, Hudson Yards. Makes sense. They also showed increased graffiti in SF since 2020, spatially mapped, which might correlate with policy changes or pandemic effects. And there were other examples too: canopy dining, new crosswalks, green bike lanes, lots of detail.
It really feels like a comprehensive tool. And you said the cost and time were reasonable.
Surprisingly so for the scale. Less than a day for the initial change detection across 20 million images. Then under 5 hours for the trend aggregation part using parallel MLLMs. And the MLLM costs were estimated under $10.
That makes it seem quite practical for, say, urban planners or researchers.
Definitely. The two-stage process is the key. It lets you use the MLLM smarts without getting bogged down by the sheer scale and cost. A real step forward for analyzing massive visual data sets like this.
So, wrapping up, Visual Chronicles feels like a genuinely new approach, using MLLMs for large-scale, open-ended visual analysis without needing labels.
Absolutely. It's finding both the trends you might expect and these really surprising ones, all backed by visual evidence from millions of real-world images. It gives you this dynamic picture of city evolution.
Yeah, like seeing the shift in retail new bakeries, closing banks laid out quantitatively.
It's powerful stuff.
Now, they do mention limitations, of course. It's mainly based on detecting local changes first, and maybe doesn't fully capture things like a change being undone or the frequency relative to a starting state.
True. And they suggest future work, like adding more stats, applying it to other visual data, maybe satellite images or historical photos, and exploring different kinds of queries. Lots of potential avenues.
Definitely makes you think, doesn't it? About all the visual data out there. Street views, satellite, social media feeds. What patterns are hiding in plain sight?
And how AI like this could help us uncover them, understand our world better.
What other visual chronicles, maybe completely unexpected ones, are just waiting there in the data to be found? A fascinating thought to leave you with. Thanks for joining us for this deep dive.